To understand what happens inside a black hole, we first need to explore how they come into existence. The life cycle of a star is nothing short of spectacular. Stars, like our Sun, are born from clouds of gas and dust in a stellar nursery known as a nebula. The gravitational forces within these clouds pull together the material, causing pressure and temperature to rise until nuclear fusion ignites, and a new star is born. However, the journey doesn't end there. The fate of a star depends significantly on its mass. For most stars, this leads to a predictable life cycle. They spend millions or even billions of years fusing hydrogen into helium. Eventually, when the hydrogen runs out, the star's core collapses under its own gravity. In massive stars, those greater than about 20 times the mass of our Sun, this collapse can lead to an explosive end, a supernova. It's in the aftermath of this catastrophic event that black holes are born. When the core collapses, if its mass is sufficient, it forms a singularity, an infinitely dense point where the laws of physics as we know them cease to function. At this point, something remarkable occurs. The gravitational pull of this singularity becomes so intense that nothing, not even light, can escape from it, creating the phenomenon we call a black hole. The boundary around this singularity is known as the event horizon, a point of no return where the gravitational pull is insurmountable. Interestingly, the process of black hole formation isn't just theoretical. Astronomers have identified several examples of stellar black holes through their interactions with nearby stars. For instance, the black hole V4641 SGR, located in our Milky Way galaxy, is part of a binary star system where it pulls material from its companion star, creating X-ray emissions detectable from Earth. This observation allows us to infer the existence of the black hole even when it cannot be seen directly. But what about supermassive black holes, those with masses that can reach millions or even billions of solar masses? These titans of the universe typically reside at the centers of galaxies, including our own Milky Way. Their formation processes remain a subject of vigorous research and debate. One leading theory suggests they formed from the merging of smaller black holes or massive gas clouds early in the universe's history. The most famous example of a supermassive black hole is Sagittarius A*, located at the center of our galaxy. In 2019, astronomers released the first ever image of a black hole's event horizon, marking a historic milestone in astrophysics. This image showed the shadow of the black hole against the bright emissions of gas swirling around it. These observations and ongoing research paint a vivid picture of how black holes emerge from the death of massive stars and evolve over cosmic time. But what happens when we venture beyond the event horizon? This is where the story takes a deeper and more speculative turn, leading us into the next chapter of our journey. Could black holes hold the secrets to the universe or perhaps connect to alternate realities? Stay tuned as we dive into the realms of the unknown in Chapter 2, the event horizon and beyond. As we delve deeper into the nature of black holes, we must face the concept of the event horizon, the point of no return. Crossing this threshold means succumbing to the extreme gravitational forces exerted by the black hole. But what really happens inside this enigmatic boundary? The event horizon marks the limit where escape velocity, the speed required to break free from a gravitational pull, exceeds the speed of light. This means that any information, matter, or light that crosses the event horizon is lost to the outside universe, leading to the famous adage, "Nothing escapes a black hole." But does that mean once something is inside, it ceases to exist? To understand this, we must reference the principles of general relativity formulated by Albert Einstein. According to this theory, gravity is not just a force, it is a curvature of spacetime caused by mass. When massive objects like black holes warp spacetime, they create complex structures that challenge our understanding of reality. Within the event horizon, the laws of physics as we know them begin to break down. Space and time lose their familiar properties. As one approaches the singularity, time itself appears to slow down due to immense gravitational time dilation, an effect first described by Einstein. For an outside observer, it could seem as if objects falling into a black hole take an eternity to arrive at the event horizon, while to them, the experience is entirely different. Theoretically, if an astronaut were to fall into a black hole, they would first encounter tidal forces. Imagine being stretched out like spaghetti, a phenomenon known as spaghettification. These forces arise from the difference in gravity experienced by different parts of the body. For a stellar black hole, they can become lethal long before reaching the singularity itself. Yet, let's entertain a thought experiment. What if we could survive the plunge and reach the singularity? What would we experience? Current theories suggest that the singularity is a point where density becomes infinite and space and time converge. This is known as a singularity and defies the conventional concepts of physics. Traditional equations break down, and we are left with the question of whether our understanding of physics is sufficient to describe the events that occur here. Interestingly, the nature of singularities also raises questions about the fundamentals of our universe. Some scientists theorize that black holes could hold clues to unifying quantum mechanics and general relativity. There is a proposition known as the information paradox, which suggests that the information about the matter falling into a black hole is not truly lost but perhaps stored in some form, preserving the laws of physics. This dilemma was famously debated by physicist Stephen Hawking, who suggested the possibility of Hawking radiation, theoretical radiation that could escape from the event horizon, allowing information to leak back into the universe. This proposition continues to spark discussions among physicists to this day. Does this mean that black holes could serve as gateways to alternate realities or even other universes? Are they portals that connect different regions of space-time? The possibilities are fascinating and mind-boggling. As we contemplate these theories that straddle the edge of science and philosophy, it's essential to remember that we have much to learn about what occurs within and beyond the event horizon. As we move to Chapter 3, we'll explore this mysterious realm further and investigate the observable effects that black holes have on their surroundings. While black holes themselves may be invisible, their influence on the cosmos is anything but. The gravitational pull of a black hole can be detected through its interactions with nearby stars, gas, and even entire galaxies. This section will unravel how black holes shape their environments and the breathtaking phenomena that result. One of the most observable effects of a black hole is its impact on nearby stars. In binary systems, when one star is a black hole, it can draw matter from its companion star. This process creates an accretion disk, a swirling mass of gas and dust that spirals around the black hole. As the material gets pulled in, it heats up due to friction, emitting X-rays that astronomers can detect from Earth. This phenomenon is the basis for the classification of some black holes as X-ray binaries. For instance, the black hole Cygnus X1, one of the first black holes discovered, has a companion star from which it siphons material, creating intense X-ray emissions observable by satellites. The interaction between a black hole and its companion star can also lead to spectacular stellar explosions when the star becomes unstable. A fascinating case is the black hole V616 Monocerotis, which showed signs of accreting material that led to an outburst of gamma radiation. These events, known as gamma-ray bursts, are some of the most energetic phenomena in the universe and occur when massive stars undergo rapid core collapse. Moreover, black holes do not just influence their immediate surroundings. Their gravitational pull can affect the motion of entire galaxies. Observations suggest that supermassive black holes stabilize the orbits of stars within galaxies and play a crucial role in their formation and evolution. In fact, it has been posited that nearly every large galaxy harbors a supermassive black hole at its center, including our Milky Way. The relationship between black holes and galaxies creates a dynamic feedback loop. As black holes draw in matter, they expel energy and momentum in the form of powerful jets emitted at nearly the speed of light. These jets can influence star formation rates in their host galaxies by heating up the surrounding gas and preventing it from cooling and collapsing into new stars. One of the best examples of this phenomenon is the supermassive black hole at the center of M87, which was famously imaged by the Event Horizon Telescope. Scientists have been studying the jets emitted from M87. These jets extend for thousands of light-years and are believed to be partially responsible for regulating star formation in the entire galaxy. The interplay of black holes with their environment exemplifies the complexity of the universe. What's even more astonishing is how black holes can warp the fabric of spacetime around them. This warping affects the path of light traveling nearby, a phenomenon known as gravitational lensing. This effect has enabled astronomers to observe distant galaxies and cosmic events, indirectly revealing the presence of black holes. As we ponder these extraordinary interactions, we must also consider the implications of black holes for our understanding of the universe. What can they teach us about the fundamental structure of reality? In the next chapter, we'll explore the concept of black hole evaporation and Hawking radiation and how it could challenge our perceptions of black holes themselves. The notion that black holes could actually evaporate and potentially disappear from existence might seem counterintuitive. However, this groundbreaking idea stems from the work of physicist Stephen Hawking in the 1970s, who proposed a theoretical mechanism that could lead to a black hole emitting radiation. According to Hawking's theory, black holes are not entirely black. Instead, they can emit particles due to quantum effects near the event horizon. This emission is what we call Hawking radiation. When particle-antiparticle pairs spontaneously form in a vacuum, one of these particles can fall into the black hole while the other escapes. The escaping particle contributes to the black hole's diminishing mass, leading to an eventual slow evaporation process. This idea introduced the intriguing concept that black holes could eventually evaporate over time. For small black holes, this process could occur relatively quickly, while for supermassive black holes, it would take billions of years. What's more, this raises profound questions about the information paradox. If black holes evaporate, what happens to the information that was once inside? The implications are staggering, suggesting that information may not be truly lost but transformed in some way. While currently controversial, this theory challenges our understanding of the principles of quantum mechanics and general relativity. If Hawking radiation is real, then it may open up new avenues for exploring the reconciliation of these two pillars of modern physics. Hawking's work has spurred numerous debates among physicists and has led to further research into the fundamental nature of black holes. Some have proposed solutions to the information paradox, including ideas surrounding black hole complementarity, where the information is preserved on the event horizon itself, while others suggest that entanglement between particles may play a role. As tantalizing as these theories are, direct evidence of Hawking radiation remains elusive. Detecting this radiation amidst the background noise of the universe is a formidable challenge. Nevertheless, the hunt for signs of Hawking radiation continues, as researchers create experiments to test these theories in laboratories and even seek observations from astrophysical phenomena. Moreover, the possibility of black hole evaporation raises questions about the fate of the universe itself. If black holes can eventually disappear, what does that mean for the fabric of spacetime? It could signal the end of cosmic structures as we know them or inspire new theories to explain the ultimate destiny of the universe. As we contemplate the implications of black hole evaporation and Hawking radiation, one thing becomes clear: black holes are not static entities but dynamic systems that evolve over time. In our next chapter, we'll delve into the search for the elusive evidence of Hawking radiation and the ongoing quest to understand these extraordinary cosmic phenomena. The quest to find direct evidence of Hawking radiation is one of the most challenging pursuits in contemporary astrophysics. While the theoretical foundation laid by Stephen Hawking opened the door to this possibility, researchers are grappling with the practical implications of detecting such subtle phenomena. One of the primary hurdles is that Hawking radiation is predicted to be incredibly weak. For stellar and supermassive black holes, the temperature of Hawking radiation is exceedingly low, making it nearly impossible to observe against the cosmic background radiation. Smaller black holes, if they exist, would emit stronger radiation due to their higher temperatures, but evidence for such primordial black holes remains speculative. Efforts to find Hawking radiation have led scientists to explore various methods. One approach involves creating analogous systems in laboratories. Researchers have been able to simulate black hole characteristics using various mediums, such as fluids and light waves, aiming to replicate the conditions around event horizons. By studying these analogs, scientists hope to glean insights that could inform our understanding of real black hole behavior. Additionally, astrophysicists are looking toward cosmic events and phenomena that may provide indirect evidence of Hawking radiation. Observations of black hole systems, particularly those that are actively accreting material, could reveal signatures of this radiation amidst other emissions. For instance, if some of the particles leaking from a black hole were identified as Hawking radiation, it could potentially validate the theoretical predictions. In the realm of experimental physics, researchers have concocted exotic setups to test the predictions surrounding Hawking radiation. Experiments involving superconductors and quantum devices have been proposed, whereby specific configurations could yield detectable signals from Hawking-like radiation. While these experiments are still in their infancy, they represent a promising direction forward. Additionally, as technology advances, astronomers are continually improving their instruments to increase sensitivity to potential Hawking signatures. For example, improved X-ray telescopes and gravitational wave observatories could help astronomers uncover new insights while searching for subtle signatures linked to Hawking radiation in black hole systems. As we navigate this uncharted territory, the potential discovery of Hawking radiation could redefine our understanding of black holes and the universe itself. The implications could ripple across the fields of quantum mechanics, general relativity, and even cosmology, solidifying our grasp on the nature of reality. In conclusion, this quest illustrates humanity's determination to comprehend the cosmos. Despite the challenges ahead, the dedication of scientists to uncover the secrets of black holes continues to push the boundaries of our knowledge and understanding. So, what awaits us as we venture further into the unknown? Join us in the next chapter, where we will discuss the implications and philosophical considerations surrounding the existence of black holes. At the heart of a black hole lies a singularity, a point in space where gravitational forces compress all matter into an infinitely dense point. This concept challenges our understanding of physics and reality itself. Let's dive deeper into what a singularity really is and why it continues to baffle scientists and researchers around the world. In simple terms, a singularity is where the laws of physics as we know them cease to function. According to Einstein's theory of general relativity, inside a black hole, gravity becomes so strong that it overcomes all other forces. This results in a region of infinite density, where space and time are warped beyond comprehension. Imagine a place where the very fabric of space-time is distorted to such an extent that conventional understanding is rendered useless. This is not just theoretical, it poses real implications for our understanding of the universe. There are two main types of singularities, the naked singularity and the one shrouded by an event horizon. A naked singularity could theoretically allow us to observe what happens at this extreme region, but such entities remain speculative. In contrast, the singularity within a black hole remains hidden from view, encased in the event horizon. Thus, we find ourselves grappling with a paradox. If singularities exist, then how can we study them if they are hidden from our observational tools? many physicists are working on theories that could bridge the gap between general relativity and quantum mechanics to help understand singularities better. One prominent approach is string theory, which posits that what we perceive as particles may actually be tiny, vibrating strings. This theory is still under development, but it could potentially elucidate the nature of singularities by providing a quantum framework for gravity. Some researchers even suggest that black holes could spawn new universes, creating a multiverse scenario. Theoretical physicist Lee Smolin has proposed that every black hole might lead to the birth of a new universe, with its singularity acting as a seed for continuation. This could mean that each black hole not only consumes what falls into it but also gives rise to new cosmic worlds. However, these ideas remain contentious and largely unproven. Scientists are still left wrestling with fundamental questions. What happens inside a singularity? How does it connect with our universe? What are the implications for our understanding of time and space? The quest for answers drives research today, illuminating the frontier of theoretical physics and deepening our wonder about the cosmos. Can science ever crack the mysteries of singularities within black holes? As we continue to explore, one thing is clear: the answers may redefine what we know about physics, reality, and our universe. Time, as we know it, is not constant. It flows differently depending on gravitational influence, a phenomenon famously illustrated by black holes. Albert Einstein's theory of relativity posits that gravity can bend the fabric of space and time. This results in an effect known as time dilation, which becomes extreme near a black hole. As you approach the event horizon, time slows down relative to an outside observer. Imagine standing near a black hole's event horizon for what feels like mere minutes while an observer far away sees you age years or even decades. This fascinating distortion of time has profound implications for our understanding of reality. Consider this: if we could harness the power of a black hole, would it enable time travel? Some scientists argue that if we could manipulate gravity around a black hole, we could potentially create a portal that allows travelers to leap through time. While this may sound like science fiction, the mathematical models support such possibilities. Practical experiments with atomic clocks on jet airplanes have already demonstrated time dilation in action. When atomic clocks are flown around the Earth, the clocks on the jets measure less time passing than those on the ground. This real-world evidence mirrors the predictions of Einstein's theory, making it easier to imagine the even stronger effects near a black hole. Yet, if we were to fall into a black hole, our experience would be vastly different. An astronaut approaching a black hole might experience the sensation of time slowing down, but from the perspective of those outside, their signal would stretch and eventually fade. This phenomenon is called spaghettification, where the immense gravity elongates and compresses objects in its vicinity. The implications of time dilation scramble our understanding of life and death. If you were to venture close to a black hole and returned, your perspective on aging and the passage of time would fundamentally change. This raises philosophical questions about the nature of existence itself. Time dilation near black holes serves as a reminder that our understanding of the cosmos is still evolving. It invites us to contemplate the fabric of reality and how our place in the universe is shaped by these celestial giants. What other secrets about time and space are hidden within the shadows of black holes? As we delve deeper, we realize that the universe has much to teach us, reminding us that the journey into the unknown is just as thrilling as the destination. Black holes are not just celestial oddities, they play a crucial role in our understanding of the universe. Modern cosmology would not be complete without considering these enigmatic entities. One of the most significant roles of black holes is in the formation of galaxies. Research suggests that supermassive black holes, found at the centers of galaxies, may influence star formation and galaxy evolution. A study published in the journal Nature highlights how the immense gravitational pull of these black holes can regulate the growth of their host galaxies. Additionally, black holes can impact the cosmic web, the large-scale structure of the universe. They act as anchors within clusters of galaxies, helping to shape the distribution of matter across the universe. By studying the behavior of black holes, astronomers gain insights into the formation and dynamics of cosmic structures. Astrophysicists also utilize black holes as natural laboratories to test theories of physics, especially theories involving gravity and quantum mechanics. For example, the Event Horizon Telescope's imaging of the black hole in M87 provided unprecedented opportunities to observe gravitational phenomena that could validate our existing models. Such breakthroughs not only inform our understanding of black holes but enhance our comprehension of the fundamental laws governing the universe. Moreover, recent studies have even suggested that black holes could be gateways to understanding dark matter and dark energy, two of the biggest mysteries in modern astrophysics. Dark matter and dark energy together comprise approximately 95% of the universe, yet remain undetectable through conventional means. Investigating black holes might illuminate their influence on cosmic phenomena, advancing our grasp of what constitutes the universe itself. Black holes present a unique challenge and opportunity. They push the boundaries of our scientific knowledge while offering glimpses into the nature of reality. By studying black holes, we venture into the unknown, questioning our assumptions and reframing our understanding of gravity, time, and existence. As researchers embark on this quest, they are not merely seeking to understand black holes but to unlock the secrets of the universe at large. As technology evolves, so does our approach to understanding black holes. The future of black hole research is poised for groundbreaking discoveries that could reshape our knowledge of the universe. One area of promising advancement is the use of gravitational wave astronomy. Since the first detection of gravitational waves by LIGO in 2015, scientists have been able to observe the merging of black holes, providing direct evidence of their existence and properties. These tremors in spacetime opened new frontiers in astrophysics, allowing for the study of black hole populations and their effects on surrounding matter. The advent of next-generation telescopes, like the James Webb Space Telescope, will also provide unprecedented access to the universe's depths. The ability to observe the early universe and distant galaxies will enhance our understanding of black holes' role as galaxies evolve. By capturing high-resolution images and spectra, scientists can collect data that brings us closer to answering questions about black hole formation and behavior. Moreover, theorists are working on developing advanced simulations to test the limits of our understanding. These simulations will incorporate the effects of quantum mechanics on black holes, striving to create a unified theory that correlates gravity with quantum principles. If successful, such models could revolutionize our comprehension of the cosmos. Public interest in black holes continues to rise, fueling funding and research initiatives. Citizen science projects aim to involve enthusiasts in data collection, while educational programs inspire the next generation of astronomers. This grassroots involvement in science brings fresh perspectives and encourages collaboration between experts and amateurs alike, enriching research endeavors. As we look forward to the horizon of black hole research, we must also contemplate the ethical considerations that arise. With immense power comes immense responsibility. The potential for black holes to be used as a means to explore scientific boundaries may warrant ethical discussions regarding the limits of human inquiry. What are the long-term implications of our discoveries? As we race toward future discoveries, we must balance curiosity with caution. The journey into the realm of black holes may not just reveal the secrets of the universe but could also redefine humanity's place within it. As we conclude our exploration of black holes, it's crucial to reflect on what these cosmic giants teach us about our universe. They remind us of the grandeur of the cosmos, the limits of our understanding, and the inexorable quest for knowledge. Black holes challenge our perceptions of reality, expanding our minds beyond the confines of our planet. They embody the mysteries of gravity, the enigma of time, and the very nature of existence itself. By pushing the boundaries of our understanding, they compel us to question everything we thought we knew. Furthermore, black holes symbolize the relentless pursuit of discovery. Scientists and researchers devote their lives to uncovering the secrets of these enigmatic objects, propelled by an insatiable curiosity. This spirit of inquiry not only drives scientific progress but also inspires generations. The fusion of science, technology, and imagination allows us to explore realms once thought unreachable. As we develop new tools and technologies, our capacity to study and understand black holes expands. Imagine what future generations will uncover as humanity delves deeper into the cosmos. In contemplating the universe's profound mysteries, we realize that every question answered leads to even more questions. Each discovery about black holes opens up new avenues for exploration and understanding. This cyclical process of inquiry reflects the essence of scientific endeavor, a perpetual quest for knowledge with no final destination. Finally, as we gaze into the night sky and ponder the existence of black holes, let's remember that they are not just cosmic phenomena. They are reminders of our own place in the cosmos, urging us to embrace the unknown and cherish the beauty of the universe. The study of black holes transcends scientific boundaries. It is a journey into philosophy, ethics, and ultimately, what it means to be human. As we stand at the edge of this cosmic frontier, we hold the power to shape the future of human discovery. The universe invites us to explore, understand, and reflect. So, as we embark on our own journeys of curiosity and wonder, may we continue to seek knowledge of the black holes and beyond, forever captivated by the mysteries of our magnificent universe. Once considered cosmic enigmas, black holes now play a pivotal role in our understanding of galaxy formation. But how did we arrive at this conclusion? Let's take a journey back in time to explore the interplay between black holes and galaxies, revealing the hidden secrets of the universe. At the heart of this story lies the discovery of supermassive black holes residing at the centers of most galaxies. Astronomers estimate that nearly every large galaxy, including our Milky Way, harbors a black hole millions to billions of times the mass of our Sun. Understanding the relationship between these black holes and their host galaxies has become one of the key pursuits in modern astrophysics. In the early universe, right after the Big Bang, a plethora of stars began to form from primordial matter. These stars, in varying sizes, lived out their lives and eventually went through an explosive phase called a supernova, leaving behind black holes in their wake. But how do these black holes influence the surrounding galaxies? It appears that they act as gravitational anchors for the galaxies. Some researchers suggest this symbiosis between black holes and galaxies is crucial for the regulation of star formation. Through their immense gravitational pull, black holes draw in gas and dust, which can lead to the creation of new stars or, paradoxically, inhibit star formation by heating the surrounding gas. A vivid example of this process is found in the case of the galaxy M87. In 2019, the Event Horizon Telescope captured the first image of the black hole at the center of M87, revealing its staggering mass of about 6.5 billion solar masses. Researchers believe that the energy produced by the material falling into the black hole contributes significantly to the galaxy's overall dynamics. This relationship is what scientists term feedback mechanisms. What's fascinating is the balance between preservation and destruction that black holes maintain. In regions where they dominate, we see reduced star formation rates due to intense radiation and outflows, while in others, they can stimulate new starbirth. This interplay is crucial for galactic evolution. New studies are highlighting the fact that black holes may influence the movement of stars around them. For instance, observations of the stars within the Milky Way's core have shown that they orbit what appears to be a black hole, with velocities that infer a significant mass concentration at the center. But what does this mean for our understanding of cosmic order? The evidence suggests that as galaxies collide and merge over billions of years, their central black holes do too. When two galaxies collide, their black holes draw closer together, leading to the potential for energetic phenomena such as gravitational waves when they eventually merge. Such events would not only change the structure of the galaxies involved but also significantly advance our study of gravitational waves, as confirmed by the LIGO Observatory's groundbreaking detections. Still, questions remain. How do the properties of black holes evolve alongside the galaxies? Do larger galaxies host larger black holes, or is there a more complex relationship at play? Researchers are delving deeper into these inquiries, seeking to unravel the mysteries of this cosmic dance. Contemplating the profound implications of these findings makes us grasp just how interconnected our universe is. Understanding black holes and their role in galaxy formation offers not only a glimpse into the past but also insight into the future of cosmic evolution. As we peer deeper into the cosmos, what other surprises await us in the dark depths of black holes? Thus, as we draw lessons from the cosmic past, the relationship between black holes and galaxies stands as a testimony to the intricate web of forces that shape the universe. What we truly learn is that black holes are not just cosmic graveyards but architects of the universe itself. Their power and mystery inspire awe and ignite curiosity as we continue our quest for knowledge. But what happens when two black holes collide? Let's explore this next thrilling chapter of our cosmic journey. Have you ever wondered how black holes relate to the invisible force of dark matter? While in the depths of a black hole, we find a realm governed by gravity. Surrounding the universe is a dominant form of matter that eludes our detection: dark matter. This chapter dives into the fascinating interplay between these two enigmatic aspects of the universe. Dark matter, as we understand it today, constitutes about 27% of the universe. This mysterious substance does not emit, absorb, or reflect any light, making it impossible to observe directly. However, its existence is inferred from the gravitational effects it exerts on visible matter, such as galaxies and galaxy clusters. Numerous studies reveal that the rotational speeds of galaxies are far faster than what we would expect based solely on the mass of visible matter. Now, back to black holes. Astrophysicists are considering that black holes might play a role in the distribution and behavior of dark matter. One of the most intriguing theories posits that black holes could serve as seeds for dark matter clumping. Some researchers suggest that as black holes grow, they could attract dark matter particles, creating a region of increased density around them. This, in turn, could provide explanations for certain cosmic structures we observe today. Consider the Milky Way. Its halo, surrounded by dark matter, could be influenced by the supermassive black hole at its center. As the black hole consumes matter, it might be altering the gravitational landscape of its surroundings, affecting how dark matter behaves in its vicinity. Recent simulations have shown that the presence of a supermassive black hole can lead to the creation of dark matter spikes, regions of high density that could explain some of the anomalies we see in particle physics experiments. Exploring these interactions opens up new avenues in both dark matter and black hole research. A particularly exciting aspect is dark energy's relationship with black holes. Dark energy, which is believed to be responsible for the accelerating expansion of the universe, could also influence the behavior of black holes, leading to unexpected phenomena. One cutting-edge hypothesis is that if black holes can act as shields that protect certain regions from dark energy, they may also give insight into how dark matter and dark energy interact. But this is not just theoretical. The discoveries made at the Large Hadron Collider and other high-energy physics laboratories are gradually unveiling the possibilities of dark matter. In search of elusive WIMPs or weakly interacting massive particles, scientists are meticulously exploring ways to connect these findings with black hole phenomena. Moreover, astrophysicists are now investigating how black holes can emit dark matter signals. With the potential development of advanced detection methods in the future, we may unlock deeper mysteries of dark matter and its origins. Do black holes serve merely as cosmic tombs, or could they be gateways to understanding dark energy and dark matter? By exploring the connection between black holes and dark matter, we are not just peering into the dark corners of our universe, we are seeking to unravel the fundamental forces that govern our existence itself. As we contemplate the complexities of these cosmic giants, the interplay between black holes and dark matter leaves us with more questions than answers. Are we ready to delve deeper into these mysteries? Our understanding of the universe is poised to evolve, and it's an exhilarating frontier we must navigate next. What do black holes signify in our quest for knowledge? These enigmatic cosmic entities have transcended the realm of science and seeped into our culture and philosophy, influencing how we perceive existence and our place in the universe. This chapter explores the profound impact of black holes on our collective consciousness. Throughout history, black holes have inspired writers, filmmakers, and artists alike. They symbolize the unknown, embodying humanity's struggle against the void. Classic science fiction, like Arthur C. Clarke's 2001, A Space Odyssey, and movies like Interstellar, have presented black holes as gateways to other dimensions and as metaphors for human ambition and exploration. These portrayals resonate with us because they reflect our fears and hopes about the universe. The notion that black holes could represent the limits of our understanding or serve as portals to new realities ignites curiosity about what lies beyond our perception. Philosophically, black holes challenge our understanding of existence and reality. They raise questions about the nature of time, space, and the universe. When we talk about the event horizon, we contemplate the ultimate limit of our knowledge. Is it the point of no return, where the known and unknown converge? Famous physicist Stephen Hawking contributed significantly to this dialogue, using black holes as a backdrop for discussions about information and entropy. He famously posited that information lost in black holes might be recoverable, challenging the fundamental rules of physics and sparking debates on what it means for reality itself. His work led to what is now referred to as Hawking radiation, the idea that black holes can emit particles, seemingly defying their own nature. As we navigate through these philosophical questions, black holes also serve as a microcosm of our larger existential queries. How do we understand infinity? If black holes represent infinite density, what does that imply about our finite lives? How do we reconcile our existence against the backdrop of the vast universe? Culturally, black holes are becoming symbols of both fear and fascination. The duality of their existence speaks to the human experience, our quest for knowledge, the fear of the unknown, and the beauty of discovery. Artists continue to draw inspiration from these celestial giants, translating the cosmic mystery into various forms of expression, igniting new discussions about our place in the cosmos. As research continues to unveil the secrets of black holes, they challenge not just our scientific boundaries but also our philosophical and cultural perspectives. These celestial entities represent a convergence of science, art, and philosophy. Our understanding of them may well redefine the trajectory of human thought for generations to come. In considering the cultural significance of black holes, we start to understand that they are not just cosmic phenomena, they are also reflections of our collective journey through knowledge, uncertainty, and discovery. So as we close in on this exploration, what lies ahead in the future of our understanding? Will we continue to be as captivated by these cosmic wonders? The mysteries of black holes may lead us down paths of profound discovery, transcending the barriers of science into the heart of human inquiry itself. For decades, astronomers have puzzled over the intricate relationship between black holes and the dynamics of galaxies. These enigmatic entities are no mere cosmic vacuum cleaners, as they play a pivotal role in the formation and evolution of galaxies across the universe. To understand this intricate connection, we must delve deep into the core of galaxies, often referred to as their central bulges, where supermassive black holes lurk. In 2015, a groundbreaking study used the Hubble Space Telescope to measure the mass of supermassive black holes in a variety of galaxies. Researchers discovered a striking correlation between the mass of these black holes and the velocity of stars in the surrounding area. This finding led to a theory called the M-sigma relation, which suggests that black holes and their host galaxies evolve simultaneously, influencing each other's growth. The implications of this relationship are profound. When black holes accrete matter, they emit energetic jets, beams of particles traveling near the speed of light, that can affect star formation in their host galaxies. These jets can create shock waves that compress surrounding gas, triggering the birth of new stars while also clearing out regions to inhibit star formation. One famous example is the active galaxy M87, which became internationally recognized when the Event Horizon Telescope released the first image of its black hole in 2019. Notably, the jets produced by the supermassive black hole at its center influenced the dynamics of the entire galaxy. Scientists believe that without the energy output from black holes, galaxies might be vastly different places, lacking the structures we observe today. As researchers continue to study this delicate interplay, new discoveries unfold. Observations suggest that black holes may influence the distribution of dark matter as well, further complicating our understanding of galaxy formation. These findings raise more questions than answers, but one thing is clear: black holes are integral to the dance of galaxies, shaping their behavior and destiny. As we explore the role of black holes in galaxy dynamics, another frontier beckons. How do these celestial giants influence the very fabric of spacetime in their vicinity? The next chapter will reveal how black holes warp reality itself, challenging our notions of the universe. The universe is a symphony of vibrations, and black holes play a significant role in this cosmic orchestra. In 2015, scientists made headlines worldwide when they detected gravitational waves for the first time, ripples in spacetime caused by accelerating masses, particularly merging black holes. This groundbreaking discovery confirmed one of Einstein's long-held predictions and opened a new era in astrophysics, allowing us to witness cosmic events that were once only theoretical. The initial detection came from the Laser Interferometer Gravitational Wave Observatory, or LIGO, which recorded waves produced when two black holes spiraled into one another and merged. This event, designated GW150914, was monumental. It not only confirmed the existence of gravitational waves, but it also provided insight into the properties of black holes, including their masses and spin rates. Since then, LIGO and its European counterpart, Virgo, have detected numerous black hole mergers, leading to revelations about their formation and distribution across the universe. Researchers have been surprised to find that many of the merging black holes are much more massive than previously thought possible, challenging existing models of black hole formation. One of the most fascinating aspects of these discoveries is how they illuminate our understanding of stellar evolution and the life cycles of massive stars. The progenitors of black holes are massive stars that exhaust their nuclear fuel and undergo gravitational collapse, but not all massive stars create black holes. The detection of gravitational waves provides a unique lens through which we can study these stellar deaths. Each merger carries a wealth of information, like the mass and spin characteristics of the black holes involved, and even the distance from Earth at which the event occurred. This has allowed astrophysicists to begin mapping the population of black holes across our universe. As researchers continue to analyze the data pouring in from LIGO and Virgo, they're piecing together a larger narrative about how black holes may be more prevalent than we once believed. But with each new discovery, more questions arise. How do these events influence galaxy formation? What are the implications for our understanding of gravity and spacetime? As we investigate the profound effects of gravitational waves, we are reminded of the mysteries that still lie ahead. The next chapter will explore the future of black hole research, particularly the innovative technologies emerging to observe and understand these cosmic giants. Will the next decade bring even more astonishing breakthroughs? The intersection of black holes and quantum mechanics is one of the most tantalizing frontiers in modern theoretical physics. At first glance, black holes seem at odds with the principles of quantum mechanics, which govern the behavior of particles at the smallest scales. However, the revelations that arise at this intersection could reshape our understanding of the universe itself. The notion of black hole thermodynamics postulates that black holes possess entropy and can emit radiation, known as Hawking radiation, as proposed by physicist Stephen Hawking in the 1970s. This radiation arises from virtual particle pairs that spontaneously pop into existence near the event horizon. When one of these particles falls into the black hole while the other escapes, the black hole loses a tiny amount of mass. Hawking's theory leads to a paradox. If black holes can radiate energy and eventually evaporate, what happens to the information contained within the matter that falls into them? This is known as the black hole information paradox, and it has sparked intense debate among physicists for decades. Some propose that information is preserved in some form, perhaps stored on the event horizon or encoded in the Hawking radiation itself. Others argue that the information is lost forever, leading to a violation of quantum mechanics' fundamental tenet that information cannot be destroyed. Recent developments, including advances in string theory and holographic principles, have provided new avenues for addressing this paradox. The holographic principle suggests that all the information contained within a volume of space can be represented as a theory on the boundary of that space, leading to fascinating implications for our understanding of black holes and the fabric of reality. The journey to reconcile black holes and quantum mechanics is far from over. The implications of resolving the information paradox could also shed light on the nature of spacetime and gravity. Will we one day uncover a unified theory that seamlessly bridges the gap between quantum mechanics and general relativity? As we reflect on these profound questions, we prepare ourselves for the future of black hole research. With technology advancing at an unprecedented pace, the next chapter will explore how upcoming experiments and observations will deepen our understanding of these enigmatic cosmic entities. At the heart of every black hole lies a region of unimaginable density and gravitational pull that defies our current understanding of physics. This mysterious core, known as the singularity, is where all the mass of the black hole is concentrated, creating a point of infinite density and zero volume. Imagine a place where the laws of physics, as we know them, no longer apply. What happens at this ultimate boundary? Early theories suggested that the singularity is a point where spacetime curves infinitely, but recent insights have challenged this notion. Researchers like physicist Juan Meldacena have proposed models suggesting that information cannot simply be lost, as traditional black hole theory implies. Instead, this information puzzle hints that our understanding of black holes must evolve. Scientists ponder, what happens to the fundamental information of matter that crosses the event horizon? Is it destroyed, or is it encoded in some way? Continuing our journey through this enigmatic realm, let's discuss the potential nature of matter and energy at the singularity. Beyond the point of no return lies a region where the gravitational forces are so immense that they could reshape our understanding of matter itself. As spacetime stretches infinitely, quantum mechanics may play an essential role here. Theories propose that particle-antiparticle pairs might spontaneously emerge, leading to intriguing phenomena that elude classical interpretations of physics. In one particular case study, physicist Kip Thorne's work on wormholes offers a fascinating perspective on black holes. Could black holes serve as gateways to other dimensions or even other universes? This concept ignites the imaginations of scientists and laypeople alike, blending the lines between theoretical physics and science fiction. Yet, these ideas remain speculative, demanding empirical evidence that we are yet to uncover. Moreover, looking deep into the implications of singularities, we encounter the famous fuzzball theory proposed by Samir Mather. According to this hypothesis, instead of a singularity, a black hole may be composed of a vast collection of strings, resulting in a fuzzy surface rather than a point-like core. This radically shifts our paradigms, suggesting that black holes might not be the destructive entities we've always thought. Instead, they could represent complex structures within the quantum realm. In contemplating these profound questions, we arrive at an unsettling conclusion. Our understanding of black holes, particularly the innermost regions, remains an ongoing enigma. The journey into the heart of a black hole forces us to confront our limitations in knowledge, igniting curiosity and further inquiry into what lies beyond our observable universe. As the scientific community continues to collaborate and push boundaries, the nature of singularities and what lies within them may someday be unveiled. Will future advances in technology reveal answers that reshape our cosmic perspective? As we continue to ponder these questions, we must acknowledge that we are only scratching the surface of black hole science. Black holes do not merely exist in isolation, they play a significant role in shaping the fabric of spacetime itself. Einstein's theory of general relativity tells us that massive objects warp spacetime, creating gravitational wells that affect everything around them. As we explore the interaction between black holes and spacetime, we see that these cosmic phenomena have profound implications for our understanding of the universe. Consider the concept of gravitational waves, ripples in spacetime caused by catastrophic cosmic events, including the merging of black holes. Detected for the first time in 2015 by the LIGO Observatory, gravitational waves confirmed a century of theoretical predictions. This discovery opened new avenues for astronomy, allowing scientists to observe black holes in a way that goes beyond traditional electromagnetic observation. Imagine listening to the universe's symphony, where every collision and merger produces a unique, reverberating sound in the fabric of spacetime. As we delve deeper, the role of black holes in the cosmos becomes more intricate. They influence star formation, regulate galaxy dynamics, and even shape the evolution of the universe itself. For instance, supermassive black holes at the centers of galaxies are thought to drive energetic jets of material into surrounding space, impacting the interstellar medium's dynamics and directly influencing the birth of new stars. This interplay highlights black holes not just as destructive forces but active participants in cosmic evolution. The discovery of the M87 galaxy's supermassive black hole, famously imaged by the Event Horizon Telescope, serves as a prime example of black holes' complexity in galaxy dynamics. As we scrutinize the dynamics of this black hole, we uncover its influence on the galaxy's structure. Researchers estimate that the mass of the M87 black hole is approximately 6 billion times that of our Sun, a gargantuan entity dominating the gravitational landscape. Moreover, using sophisticated simulations, scientists are mimicking the effects of black holes on nearby stars and gas clouds. These models reveal that the gravitational pull of a black hole can disrupt the orbits of stellar objects, leading to fascinating phenomena like tidal disruptions. This dynamic relationship showcases the violent yet elegant ways that black holes shape their environments. In one striking case, astronomers observed a star spiraling dangerously close to a supermassive black hole, creating what many describe as a stellar demolition derby. This event, captured by the Hubble Space Telescope, provided critical insights into the forces at play during such encounters. As we contemplate the influence of black holes on spacetime and the cosmos, we must also consider the philosophical implications. What does it mean for the fabric of reality when objects can warp space and time? Does this phenomenon challenge our understanding of causality and the linearity of time? When we gaze into the depths of a black hole's gravitational well, we are not merely looking at a cosmic vacuum, we are staring into the heart of the universe's most profound secrets. As we deepen our exploration, we recognize that every black hole offers a window into the fundamental nature of reality itself, pushing us to question the very essence of existence. For decades, astronomers have been grappling with the elusive nature of dark matter, an invisible substance that makes up approximately 27% of the universe yet remains unseen. Though its presence is inferred through gravitational effects on visible matter, the true nature of dark matter eludes detection. In our quest to understand this cosmic puzzle, black holes have emerged as potential clues. One intriguing hypothesis links black holes to dark matter